Hello, everyone. You guys made it through the rain. Hopefully, not too many of you are caught in that downpour right before class. So, welcome back. Today, we're going to talk about units and mass balance. Some of this is just going to be straight up review for you, I hope. Some of it will be a little bit new, and then we'll start touching on some things that maybe you haven't looked at problems in this sort of a way, but what we're doing today is still going to be kind of on a simplified level, and it'll prepare us to go deeper the next, in this course with that stuff. Yeah.
Are you going to be able to send us these lectures since we don't have the Moodle thing up yet?
I'm working on it. I don't have access to Moodle yet, so I don't have access to even your emails necessarily. So I apologize. I will post them as soon as I can. And I will post all of the slides and the lectures to Moodle. Right now, if you want to, and I'll write this on the board later as well, if you want to see this lecture or the past one, they'll be on twitch.tv/snowslab. In fact, we are there right now. I'll show you. Will be a little bit of a Inception sort of experience here in a moment. So this is where I'm live streaming, and you'll see it's just going to be Inception here for a minute, and it'll make your brain hurt if I let it sit here, especially if I had the sound on, because that would be bad. All right, so I'm going to stop that before it gets too crazy.
It's so fun.
And in case you're curious, I'll show you what I'm looking at on my screen while I lecture. Is well, I see the slides normally because I'm seeing what's on the right pane with this. Oops. All right. Let's see if I can grab the screen itself. So if you chat to me, by the way, if you do have to miss for some reason, that'll show up here, and so I'll see you. What's that? Enable Twitch drops and stuff. If I could type and write at the same time. So there we go. Got it. Great. Okay, so anyway, that's just a quick little bit about how I'm doing this, and to clarify just a little bit, my expectations are attendance is in person, an absence. So if you have to miss class for some reason, let's say your car breaks down, normally you might not contact your professor and like, well, crap, I'm just screwed today. Well, email me, let me know what's going on. That way I know you're participating. And if you do sign in here, say hello in the chat. I think you have to make an account or whatever, but please do that and ask any questions as you go. That'll let me know that you are participating, and that'll keep us having a reasonable amount of participation in class here as well. That's what my aim is. I think in-person instruction is going to be better, but I like the flexibility that I built in with all the COVID stuff. So it's going to be there for you as an extra resource and for those moments. So I also learned recently that it might be possible if I was sick but still felt like lecturing, I could do so from home and we'd just use this. I like it a lot better than Zoom because then I don't have to, there's far fewer distractions and I can do fun things with my cameras. I've got an aquarium, we can do a little chemistry, check the pH, it's kind of fun. Anyway, so today, I'll write that on the whiteboard in a few minutes as well, but you can get it there. I'm going to be trying my best to get access to the Moodle so I can email you guys and so I can post all of this stuff. You'll certainly have it there as soon as I can. All right, so then any other questions before I get to the class material today? All right. So units and mass balance. Like I said, a lot of this should feel kind of basic or almost years ago kind of stuff. But I'm going to stress them because it's going to help you throughout the course, especially if you haven't worked with similar types of problems. I know a lot of the civil engineers, you do all sorts of highly rigorous calculations for all sorts of situations, but you haven't really seen the kind of, okay, well, how's the concentration changing here type of a problem. And most of it does boil down to the units. So if you know the units, or you have a good grasp on manipulating the units and understanding where they are, you're going to be able to then make sure that you are properly conserving your mass and properly setting up your equations to solve the different problems. Okay, so anytime we're dealing with a mass balance, really what I mean by that, it's not quite like a balance scale like this, how much is where. It's more so mass over time. So anytime we're dealing with a system, it's typically an active system. We've got maybe a container with some reaction happening, and maybe some water loss when I didn't have the lid on tight enough, or maybe we have a container with no water loss. So there's no loss of water, but maybe some reaction is creating or destroying some bacteria or some chemical inside, right? So then we're concerned then about the change in mass of that particular stuff, the chemical, the bacteria, whatever it is, over time. How long do I need to sit there shaking until it's ready to drink, or whatever? So this is all pretty much always going to be some concentration per time, or ultimately a just mass per time unit. I'll elaborate more on that and what I mean by a mass balance in the context of some sort of a reaction or reactor in a little bit. A lot of the stuff we're going to use is chemistry based, so we have to just a quick reminder here that really chemistry is a matter of units, and I think I mentioned last time that I'm going to help you by simplifying it down to that level so we can talk about these topics that may have annoyed you in the past, or maybe it's been 5 years since you've seen chemistry, and now you can say, okay, well, this is a simple way to look at it. Hopefully I can handle that. And really the most advanced chemistry stuff is a little bit of chemical equilibria, and I'll walk you through that as we go. Okay, so with that, I want to touch on a few basics that I expect of you to know. SI units, I'm sure you've seen them. I'm sure you've seen the prefixes, at least most of them. There's definitely some that I would expect you to not have any issue with if you saw it on an exam. For example, a kilogram, right? I definitely expect you to be able to say, okay, kg is 1,000 grams, right? You should know that. If you don't, this is here. You can take a look and study this. Even over here on the right, it gives you specifically that example, kilogram, kg, 10 to the third grams, right? Likewise, we don't see hecto or deca very often, but the concept applies. Deci, like decimal. So I would say kilo, centi, milli, micro, and even down to nano, you should know off the top of your head, right? Nano might be a little unfamiliar, a little new. It's one billionth, right? So 10 to the 9th. Micro is 1 million, 10 to the 6th. Milli is 10 to the 3rd, or 10 to the minus 3rd, rather. All these minus. And centi is, of course, hundredth. So I expect you to know those. So just take a minute to take a look. The units as well, or the symbols. I mean, micro is a mu. So if you see the mu m, for example, micrometers, you should know that 1 micrometer equals 1 times 10 to the minus 6 meters, right? So very basic, just a quick reminder, refresher in case you need it. Speaking of units, I'm giving you this specific table for your formulas on your exams. I'm giving you a couple tables, periodic table, this table, and then some formulas. Again, I'll post those to Moodle as soon as I get access. Then you'll have those as a study guide to know what you have on your exams and what you're going to have to commit to memory. And so with this, I'm stressing the units because sometimes we'll take a look at water at 5 degrees Celsius, and we'll say, okay, well, let's solve some sort of problem. It's got this density, so you check the units, the density here, kilograms per cubic meter, and then you're going to need the dynamic viscosity. We use that a fair bit. And so you might say, okay, well, this dynamic viscosity, excuse me, also using mu, sorry for that confusion here, but you might think to yourself, okay, that's 1.518 kilograms per meter second. But you'd be wrong, because you missed something important. Part of the units there is the 10 to the minus 3. Okay, so make sure you pay close attention to that, because here it's 1.518, and that 10 to the minus third is built in there. And you'd be off by a factor of 1,000 if you weren't giving attention to your units there. Okay, so just a little warning. It's a nice little table. I don't mean to be tricking you, I'm trying to make this obvious, but good exercise in paying attention to your units. And you'll see this in a fair amount of plots or different things. Some of the others, we don't really use the other terms here much at all, but the kinematic viscosity is a 10 to the minus 6, and so on. Okay, so a couple more kind of handy unit conversions that you should know, and I'm going to go over here. One in particular, how many liters are in a cubic meter? The answer here is 1,000 liters per cubic meter. That's not something maybe you knew off the top of your head, but it will be good to know off the top of your head because it's going to be a little bit annoying to convert on an exam. One thing to do is to think about, practically speaking, what does that look like? So this bottle is 1 liter, and you can pretty easily visualize 1 meter, right? You know it's like about a yard something. So if you just imagine for yourself, you take some bit of space and cube it. How many of these water bottles approximately is that going to fill? It's going to fill it, right? Is it 10? Is it 100? Is it 1,000? So on, right? So if you think about it, 10 of these, no way that's going to fill this whole meter, right? This full cubic meter. Okay, well, 100. Well, you could start thinking about it, and maybe you get kind of close, but it's still kind of off. And then when you think about really how far it is, yeah, that's not going to do it either. So it's always worth checking yourself and checking kind of how you're thinking about a problem, just with tangible, practical knowledge, if you can make some sort of a relation, right? So think about the bottle of water and make that connection. Okay, so that's just a kind of a given, and we could derive that from the density or some other term. Likewise, there's 1 milliliter in 1 cubic centimeter. So 1 milliliter of water, it's a pretty small little bit. That fills 1 cubic centimeter. So again, you might think to yourself, all right, well, we know that a centimeter is smaller than an inch, probably 2.5 times smaller. And so that gives you some conception of how much water or how much liquid that would be. Okay, so I have a quick challenge for you. How many grams are there in 1 milliliter of water if our density of water, which we can grab from the previous page here, is exactly 1,000 kilograms per cubic meter? So take a moment to think about that and to solve that. Kilograms. What's that? I'm not going to make you do angstroms, no.
Okay, thank you.
But an angstrom, though, is 0.1 nanometers. So it's not too far from a relatively normal unit.
When I took Chem at LC, they were like, yes, you have to remember this. This is going to be used for the rest of your life. And I was like, I don't know. Concrete here, we do tons.
Well, yeah. If you looked at the microstructure of concrete, maybe, like how far is one atom from the other? You could get into crystal structure stuff, then you're dealing with angstroms, but probably not. so I'll walk you through how I would do this. I have a question online, actually, a good question. So will the lecture notes be posted before class once Moodle is open? Yeah, my intention will be to post the blank notes before class and then fill them out as you go. So in the future, hopefully you should be able to follow along with your own notes like this if you'd like. It's a great example of somebody participating online. So they post a question. You guys can't see it, but I can read it out to you, and that works great. So thank you for that. Okay, so I'm gonna. There's a few ways you could solve this. I'll just take you through the one that strikes me as reasonable here, or that makes a lot of sense. So since we know 1 cubic meter is 1,000 liters, I'm going to say the density is 1,000 kilograms per 1,000 liters. So it's kind of saying the same thing there, which means we have 1 kilogram per liter, which is actually kind of how we define mass in a sense. So at 5 degrees Celsius, if we have a known volume of water, we say that's 1 gram, or that's 1 kilogram or whatever. Okay, so from here we can say that's 1,000 grams per liter, or we could go ahead and convert to milliliter because we know it's 1,000 milliliters in every liter. Now I could be a little more elaborate here. I could say this 1 kilogram per liter and then multiply, sorry for the mess, and say, okay, well that's 1,000 grams per 1 kilogram, so that I can carefully cancel my units. And then I can also say that's 1 liter contains 1,000 milliliters and cancel the liters, doing effectively the same thing here. I'm just shortcutting a little bit. So this ends up yielding us 1 gram per milliliter. Okay, so turns out just 1 gram in each milliliter. Now, this brings me to a kind of something that may not have noticed here. In a way, it seems kind of weird that we have 1,000 liters per 1 milliliter, 1 cubic meter, but then 1 milliliter is a 1 cubic centimeter. At a glance, you might think to yourself, oh, why isn't that 1 cubic millimeter, since it was, we're dealing with thousands here. And the reason is, just a quick reminder for you that when you're squaring or cubing units to say, let's say 1 meter, and you want to convert to cubic meters, let's use centimeters. Let's say 100 centimeters equals 1 meter. And if you want to convert that to compare cubic meters or cubic centimeters, you can't just convert the units and call it done. You have to cube outside of the units, outside of the number. So when we cube each of these, that becomes 100 to the third power equals 1 to the third power centimeter cubed or meter cubed, right? So that's keep that in mind whenever we're dealing with volumes or areas that we need to convert. So again, like I said, very straightforward unit stuff, should be just review. The next topic is numbers to mass. So this is essentially what the molar units for are in chemistry. That's also what 1 dozen does for us. So 1 dozen is just like 1 mole. It's 12. It's 12 of something, right? A dozen eggs, it's 12 eggs. A dozen beignets, it's 12 beignets, right? 1 mole of atoms is 6.02 times 10 to the 23rd atoms. You could have that many eggs. That would probably be larger than the Earth. So it's just a convenient number for specific activities, right? A baker's dozen, 13. It's like you made 1 extra for a taste test. Okay, so really, the number to number ratios are important when it's a corresponding reaction or something that depends on how many of the thing there are. So I'll give a kind of a humorous example of that in a minute. Okay, so concentrations then can be any type of unit, essentially. We just are looking at some amount of stuff in another amount of stuff, right? Oftentimes, if we're doing something chemistry related, we can see, okay, how much color is there, and the higher concentrated it is, the more color we have. That's one of our laws in chemistry, is that generally that light absorption corresponds directly to the amount of that substance, which is very convenient for a lot of chemistry. So we have different denominators we can use. We can use volume, we could use mass, could use mass, yes. The volume could be liters, could be cubic meters, could be a percentage. We're doing a percentage by volume, meaning, in here, about 80% of my container by volume is water, the rest is air. Or you could be thinking, okay, in just the liquid phase here, if I added some alcohol, then I might have 10% of the volume is ethanol by volume, right? You'll see that on any alcoholic beverage label to have some percent by volume. You could technically do it percent by weight. I think that's less common. So you could do the mass of, let's say, milligrams of gold per kilogram of soil in a mining operation or something, right? You could do a contamination in soil or in water or in some mixture. So we have all sorts of concentration units we can use. It just, again, it depends on kind of what system we're dealing with. My point here is to call your attention to the fact that we might face different ones, but it's kind of operating the same thing. We're looking at some smaller amount of stuff. We can usually think of it as a concentration being a solute dissolved in a solvent. So that would be like salt in water, or maybe we're looking at gold particles in a soil, and the soil we're calling, that's not really a solvent, but it's the mixture that's containing it. The point is the small thing in the total mixture. Okay? Whatever concentration we're dealing with, that's the essence of it. A quick note on the parts per X. So we're all pretty familiar with percentages and how to work them and all that. When you see something that calls parts per thousand or parts per million, parts per billion, these are essentially just percentages just with a different denominator. So you will see these occasionally in the class. You'll see them in environmental systems, if not other places in science and technology. But essentially, when you say we have, let's say, I think in our atmosphere right now, we have around 400 ppm of CO2 in our atmosphere. Okay? Essentially what that's saying is that's 400%, except it's not percent, it's per million. It's not per 100, it's per 1 million. Okay? So that's 400 parts by volume per 1 million total. Okay? Yeah.
The parts per, is that always just assumed volume, or could that also be grams?
It definitely could be mass, so mass per mass. Just like percent can be by weight or by mass. But usually it's going to be volume. And I don't even know how much we'll use it in our class, but I want you to be prepared in case you do see it on a homework or something. You ought to be familiar enough to use it. Okay? So just think percent, except you have to adjust to, instead of percent meaning per 100, because the cent is the 100 Latin prefix. We have million or potentially thousand or billion or even trillion. Okay. So to come back to the issue of molar units and number conversions. So the real analogy I'd like to let stick in your mind here is if you think about being naughty and egging a car, you don't consider the mass basis, right? You don't think, okay, well, how much does this car weigh? Is it 1 ton? Is this like 1.5 tons? Okay, how many eggs do I need then? I guess I need a 1 ton eggs per. No, you don't do it that way, right? I've never done it, but I can imagine if I was really going to be scientific about it, maybe I would say, okay, well, 1 for every door handle, and maybe 1 for every window, right? So then it's some number. It's maybe a dozen per car, right? It's a numbers basis, not a mass basis. So sometimes it's important, and the end result really is egging yourself because it's just a dumb activity to do. But the end result is we have situations in life sometimes where you want a number comparison, and chemistry is often that way. We have a reaction that must have molecule A and molecule B in order for it to occur, and so we have to compare on numbers rather than the mass of them. And sometimes some chemicals are very large and are going to weigh comparatively to, let's say, a hydrogen atom. It's going to weigh essentially the comparison of a car to an egg, right? And so it really does not make sense to compare on mass unless you've already factored in a conversion for, okay, well, how many are there? So that's the whole reason we have molar units in a nutshell. Okay, so if it never stuck with you before, maybe the egg will stick. Okay, so just like a dozen, mentioned this already, 1 mole of X is this number of X, 6.02 times 10 to the 23rd. You don't even need to remember that. I just want you to know that this is a numbers conversion. We're going from number to mass with this number, or we have a tool to do so. 1 dozen of X is 1.2 times 10 to the 1 of X, right? So you already know how this works. It's nothing unfamiliar. It's just maybe you haven't thought of it in this manner. Okay. So speaking of molar units, how do we do that conversion? Well, the mole lets us take what we see on the periodic table, this number down below. This is hydrogen here. Essentially 1, with some little bit of a decimal change there. Essentially 1 mole of this substance is going to weigh that many grams. Okay, that's our shortcut. So this is the atomic weight, and the mole conversion lets us take atomic weight and convert it straight into grams. Okay, that's what the dozen type of a unit does, except it's a mole, not a dozen. So 1 mole of hydrogen, that's 6.02 times 10 to the 23rd hydrogen atoms. That weighs 1 gram, or that is 1 gram of mass. Technically 1.00794. Okay, does that make sense? We good on that? Hopefully it's just a review. When we talk about molar concentrations then, we're doing moles per liter is our standard. That is an SI unit. That's capital M is the abbreviation for molar units. So how many moles per liter? Capital M, if you see that, you know that is moles per liter. So commit that to memory in case it's not there already. The other thing I'd say is anytime you see a brackets around a chemical compound, so the brackets around nitrate here, NO3 minus, those brackets mean we're describing moles per liter. Okay, so anytime we have an equation that has brackets, you might be given some mass concentration, so milligrams per liter of chlorine, but then we need a chemical equilibrium, and the formula for that has brackets. We have to convert so that we are on a numbers basis, so that we have the appropriate relationship for the chemical reaction. Then, sometimes you might have to convert back to mass if you're trying to figure out, okay, well, how many kilograms of this chlorine do I need to add to my swimming pool to achieve the desired result? Depends on the chemistry, so you have to convert to moles, and then when practically you're holding it in your hand, you're like, well, I don't know how many a mole is, but I could weigh this and find a kilogram, right? So we have to convert back and forth sometimes, just the way it is. So the brackets, keep in mind, that's always going to be the molar units, moles per liter. So that's probably the most of the chemistry that if you get that solid, you're going to be almost completely set for the course. Okay, sounds pretty simple. Just make sure that this part is you can do that, because if you can do that, you can manage the units back and forth from mass to moles and know when to do so. That's almost everything you need to know, and we'll cover the other stuff as we get to it. Okay, for one other type of number manipulation concentration I want to point out is our units for disinfection. You will have seen on a bottle of Lysol or bleach or whatever, it'll say kills 99.9% of germs or whatever. That does not mean that researchers have taken every single type of germ that's in the environment and tested it, and hey, look, it killed 99% of all the different types. No, that's not what they've done. They've taken a particular bacteria or virus, and they put some on a little petri dish, and they exposed it to some of this chemical, and then they gave it a certain amount of time, and then they measured and said, okay, well, we started with 100, and now we're left with just one. So it killed 99% of them. So they just take one particular thing. This is actually something I do a lot. We do in my research lab is disinfection experiments. So we literally count on little petri dishes how many bacteria or viruses are left over after some process. Of course, we have to grow them so that we can see them visibly. It's kind of a neat tool that we can do. But really, it comes down to how many did we start with, and then how many are we left with. So, how do we manipulate these? Well, first of all, typically when we have some sort of a petri dish and we have little growths of bacteria randomly, we're essentially counting the colonies of bacteria or plaques of viruses. And so our units are going to be colony-forming units, which we expect is pretty much one bacteria. Maybe if two were sticking together, we would count that as one because it would just come out in one colony. So sometimes, to be a little more precise, we'll just leave it as colony-forming units because we don't know for sure, but the assumption is it's approximately 1 to 1. So colony-forming units per liter, and we get that by doing some dilutions, pouring it on a plate, and seeing how many grow. The virus method is very similar. I could tell you more about that if you're interested. But essentially, we're also counting little plaques that grow on whatever cells we feed them. Okay, so then we check that before and after some process, and we say, oh, okay, if we had 10 on this plate to begin with, and then like 2 later, that's our N initial, the N not here, and then the N final. This is a concentration. So the N is our concentration. That's some number that we count per volume that we exposed to our petri dish, some volume that we used here. So it's a numbers concentration. Okay, so I'm going to give you an example here of specifically what that looks like. A lot of times we'll measure or quantify our disinfection in terms of initial versus final. And that's really where the 99% comes in. So if we take our initial number, well, really our final divided by initial, so initial is the comparison, this is going to give us the fraction that is remaining after we do some sort of disinfection. Okay? So if we're removing them or killing them, N over N naught gives us that portion that remains afterwards. That means that if we were to kill 99%, that means N over N naught should be 0.01, because 0.01 is the fraction root that are still there. Does that make sense? So then 1 minus N over N naught is the fraction removed. So 1 minus N over N naught, in this case, would be 1 minus 0.01. That gives us that 0.99, and we can convert that to a percent just multiplying by 100. So that's where the 99% is coming from, by comparing how many we had at the beginning versus how much we had at the end. So then there's a common phrase that we use. We call it a log reduction for every decimal place we go. So if we had a 99% removal, we would call that a 2-log reduction. So the reason we call it log is for logarithm, right? Logarithm base 10, if you carry that, if you say the log of 0.001 is minus 3, that means 10 to the minus 3 equals 0.001. So that's what it's coming from. So a 3-log reduction is a 99.9% removal. Okay, so you're going to see these problems on exams or on homeworks that say, what does it take to achieve a 3-log reduction? Okay, so this is another small little piece of knowledge that I'm expecting you to have on hand for the class. This type of terminology. It's very common in the field. It's just one of those language things. Makes pretty good sense once you take a look at it and stop and think about it. But if you have not done so, you might feel a bit lost. Okay, does it make sense? We will end up using, in several situations, this type of n over n naught. Sometimes we might flip it if we need to compare. When we do particle flocculation, we'll have many particles and then they're sticking together into fewer larger particles. It's going to be a little bit, it's going to be the same type of manipulation to see, okay, what did we have beforehand and what do we have afterwards? Okay, so let's get to mass balances then. When I say mass balance, again, what I'm talking about is some sort of mass per time. So we're looking for a way to understand a system on the principle of conservation of mass. That way we can design a system to say, okay, we need that 3-log reduction. What are the conditions we need to achieve that, given some sort of constraints? Maybe we only have a certain square footage to work with to build a reactor. Okay, so how intense do we need to shine the UV light, or how much chlorine do we have to add in order to achieve it with that given volume that we can get? Whatever the constraints are, we're going to develop a mass balance in order to establish the system and understand what we need to do. So the accumulation rate in a system like this, we have some volume. We've drawn a control boundary. So this circle here, we would say that's our control boundary. And we're interested in whatever is going in or out of that and any reaction that's happening inside of that. So we need to know then, the boundary gives us the edges to say what's coming in and out. And we also care about whatever type of reaction might be happening. So for a system like this, if we have a flow rate Q and some concentration of a chemical C, we'll say Q is the flow rate. And C is a concentration. Then we have right here the concentration times the flow rate. That's going to give us a mass per time, because the flow rate is going to be a volume per time. If we multiply that by the concentration, which is a mass per volume, we can see that the volumes are going to cancel, and we have a mass per time term here. Okay? So when we have a flow rate and a concentration, if we multiply them together, that's an input rate or an output rate. So we have an input rate here of Q times C, and we have over here, let's say, the same flow rate going out, and you know what, we're going to call this C initial, C naught. And we have the C final coming out the other end. So in the system, if there's no reaction, then the accumulation rate inside that boundary should be 0 because there's nothing changing the amount of concentration. So in some systems, accumulation is just going to be 0. In the case of water flowing through, if I would just have water flowing into my bottle and out, nothing's happening except the water's flowing. I'm not expecting any chemicals to accumulate in there, right? If I had something separating, maybe stopping particles, then I could say, okay, particles are accumulating. Then I'd have an accumulation rate, even if I've got a steady flow. So something has to change in here. Maybe I have water flowing in to what's the Dead Lakes? What are they called? The Dead Sea. Water's flowing in, but there's no outflow. It's just evaporation taking it away, which maybe we could call that a reaction. Okay, so evaporation as a reaction, removing water. Essentially, what's happening is the water might stay the same, but all that salt that's coming in from the water that's flowing in with it, or whatever sediment and stuff, that's getting concentrated because we have more salt added, making it a really, really hypersaline environment. The water is just being removed by evaporation reaction. Okay, so that's an accumulation of salts and other stuff. But most of the time we don't have that situation. Most of the time we just have water flowing in and out. So unless there's some sort of reaction in here, then it will be could be that accumulation rate is 0. When it is 0 for a flow-through system like this, we call that steady state. Maybe we do have a reaction. So maybe we do have a reaction happening here, and then the concentration coming in is different than what's going out because the reaction is creating or destroying this material. Then we still could have steady state, but that just means some of our chemical is destroyed by the reaction, and some of it's leaving in the flow. Okay, but we could have 0 accumulation, meaning we have the same amount of mass of this chemical coming in as is being destroyed or leaving over time. Okay, so that's what I'm talking about with steady state. We'll give more examples. When we write a mass balance, what we do is we say we have some accumulation rate. That's oftentimes what we're interested in, or we can set it to 0 depending on the case. This is a mass per time. How is the mass changing per time? We will write that typically as dc dt times the volume. So the change in concentration over time in the volume that we've defined. That's going to be equal to the input rates minus the output rates plus whatever reactions we have. So that'll be a plus the growth rates, so anything that's growing the chemical or the bacteria or whatever, minus any death or decay rates for whatever's there. A lot of times we won't have, let's say, growth rate, and it'll just be input, output, and a decay rate. So we're going to build towards being proficient with setting up a mass balance like this, understanding what types of rates are happening so that we can mathematically build this equation and then use algebra to solve it and then get an answer. Okay, so that's the core of most of the class here. And each of these, by the way, is going to be mass per time. So when we talk about our reaction rates, these will also be mass per time. So each component is going to be mass per time. That's a good way to check your work, to say, okay, did I start this correctly? Is this a valid mass balance? Well, it should be mass per time at the end of the day. Maybe sometimes it'll be number per time, but I think you get the picture. And in this particular drawing here, we would say, let's say we have a negative reaction. So it's a decay reaction. So this one, we would say the accumulation rate, dc dt, times the volume is going to be equal to the inputs, QC naught, minus the outputs, QC, plus the reaction, which is a negative. I'm going to leave it as the volume times a reaction of C. Okay, we'll elaborate on that later and expand what is that R of C. Okay, you'll be able to fill that in according to a given problem, but for the moment, I'm just going to leave it like that. That's the mass balance for this system that we drew. May or may not. I mean, I guess I said it has a negative reaction, and we put it right there. Does that make sense? How many of you seen this sort of a way of looking at a problem before? Is this kind of new? All right. Okay. So hopefully this is helpful then. Okay, so a very simple problem example for you here. I'm going to give you a couple minutes to solve it. I'll read it with you first, point out a couple things. So we have a stream flowing at 10 cubic meters per second, has a tributary feeding into it with a flow of 5 cubic meters per second. The stream's concentration of chloride upstream. Chloride, by the way, is just Cl minus. Like sodium chloride is the Cl minus part of that. Okay. The stream's concentration of chloride upstream of the junction is 20 milligrams per liter. The tributary chloride concentration is 40 milligrams per liter. So treating the chloride as a conservative substance, that's a key word there, meaning that there's not going to be any reactions. So there's no reaction term, greatly simplifying the problem. And assuming complete mixing of the two streams, we'll talk more about ideal reactors later, find the downstream chloride concentration. Okay, so that's your task. We want to find that value. So I'm going to give you a couple minutes to think about that. This is a type of word problem that maybe you could do on your own without even ever thinking about this class, but think about it in the frame of reference of setting up a mass balance, right? So the accumulation is going to be the input rates minus output rates plus whatever reaction. And consider that whether or not it's going to be steady state. Because steady state would make the accumulation 0. So All right. So for this problem, we were given that the streams are flowing together, they're mixing, and carrying on their way as one larger stream. And we're also given that it's a conservative pollutant, meaning no reactions. So really, I don't see any way accumulation could be anything other than 0 here. So it would be safe to say accumulation is 0 and say that as an assumption if you had to assume that. But really, with no reaction and nothing else that's happening here with, I gave the Dead Sea example, like there's no water being lost or added somehow mysteriously here. So really nothing can change. So it's just flowing through. And if you just have water flowing through a junction, you're going to be at steady state, right? Unless something's changing and no information was given about that. Sorry about that. Okay, so accumulation should be 0. And so then we could say 0 is equal to the inputs minus the outputs. And even before we get going, could even just be simpler to say, well, first of all, there's no reaction. So plus 0. We could just say inputs are equal to outputs. And as a side note, if you ever are getting confused with the growth rates versus decay rates and how to use their signs here, another way to look at a mass balance is if you are at steady state, you could say that inputs plus growth reactions together are going to be equal to the outputs plus any decay reactions. So that's another shorthand that might be useful at some point. And you could say, okay, well, that's how I know how to set up my system. I know I don't have any decay, but I do have a growth, so I'm going to write it out that way because I'm at steady state. Okay, so anyway, with this, we say inputs are equal to outputs. We know the inputs are going to be QSCS plus QWCW. That's going to be equal to CMQM. Okay, so that makes sense. Inputs equal to outputs. We just add the inputs together. So from there, the thing we're solving for is CM. We have everything else. This is, 10 cubic meters per second times 20 milligrams per liter. We add to that the 5 cubic meters per second times the 40 milligrams per liter. And I really would encourage you to write your units out, at least the first step as you're assembling your mass balance. A lot easier for you to track them that way. It is a little cumbersome, but it's a habit well worth making. We can say that's all equal to CM and QM. We actually don't have either of those, so we have to stop and think. Well, the QM is pretty obvious if you think about it, because we have 2 flows of water, no hint at anything weird happening to the water. So the 2 flow rates are going to combine and add together, right? So the QM should just be the 5 cubic meters per second plus the 10 cubic meters per second equals 15 meters per second. Okay, does that make sense? So that would be the one potentially tricky part of this problem, is just recognizing that you actually have to kind of consider the problem to get that part. Okay, from there, we can add these together. Essentially, we have 200 plus 200 here. And since I'm going to divide by the flow rate to solve for CM, the units are going to cancel nicely. And so I'm just going to say 200. You could write them all out and say cubic meters, milligram per second liter, plus 200 of the same. But we're about to divide by the cubic meters per second anyway. So I'm just going to say CM times 15 cubic meters per second. So that yields a value here of 400 divided by 15. And I did this with my class earlier. Should be 26.6 repeating, right? So 26.7 milligrams per liter of chloride. Does that make sense? Is that what you got? Okay, so like I said, this problem you could have done without anything learned from me. I would expect you probably could have done that. But hopefully what you'll notice is as we start taking this mass balance approach, even for a simple problem like this, it'll let us build and expand to more advanced problems. So any questions on how the mass balance worked or anything? Okay. All right, so I want to start talking about reactions, reactors, and then get into the kind of a true chemistry review. We did a little bit of review today, just kind of warm up. We'll go through some more basics, probably the next lecture or two. So when we're talking about a reaction, it doesn't have to be a chemical reaction, could be biological, like we see here. We've got lots of air bubbling through this activated sludge tank. That air is providing mixing and providing all these bacteria with plenty of oxygen so that they can eat all that food that's there. We want them to have as much oxygen to do as much respiration and reproduction as they possibly can. It gives us a great advantage because the bacteria can take molecules from the water and create particles instead, because bacteria are particles. So they're doing a nice separation process, taking something that's really hard to filter or to grab out of the water and just converting that into some particulate matter. And they're also just generally decomposing stuff, which is also helpful. So when we talk about any sort of a system, we're gonna have two things. One is the actual reactor vessel itself, and separately is the reactions that might be happening within. Okay, so they do not depend on each other. We might design the reactor based on the type of reaction we want or we have, but there's no reason that because I have this little bottle that's going to act like what we'll call a batch reactor, there's no reason that has to be a specific reaction type or reaction order. Okay, so the physical container that's going to be separate from the type of reaction we have inside. I say that because I want to talk about the 3 different classes of reactions that we're going to look at, that we're going to put into different reactor vessels. Okay? So for reactions, really what we're talking about is reaction order. And then, of course, there's direction. It could be growth or decay. So reaction orders are really talking about how the reaction itself depends on how much stuff you have in there. For example, if we have a 0 order reaction, a decay reaction would look like this. The concentration would change linearly with time, or a growth reaction could look like that, where we have some sort of a slope and it's a line. Okay, the stuff is changing with time, concentration changes over time. That's what it is. Okay, that's a zero order reaction. A first order reaction is going to be an exponential change over with time. Might look like something like that, or something like that. And the reason that's exponential is because the rate at which it changes depends to the power of 1, so it depends one time on the amount of stuff that's in there. We'll give you a very tangible example for that in a moment. Finally, our second order reactions are very sharp, very rapid, and depend quite a bit on how much stuff you have in there. So probably didn't draw that particularly well. Something like that. Okay, so a first order reaction versus a zero order reaction. Using evaporation as an example again, if we just have some surface area that water is exposed to the air and we have some amount of water there, say we keep the conditions pretty constant, usually we can expect some constant amount of evaporation over time if we have, let's say, like a bottle like this where the surface area is not changing, right? It's just, we have this one little layer, it's a few inches in diameter, we have some evaporation rate. That's, let's say, a gram per day of water just lost if I leave the cap open. That's a set amount over time, and that's going to keep happening until it's gone, okay? It would also be like adding $100 every month to a bank account, right? It's like a flat amount, you're adding it for a growth reaction, and you just add that much every month. It doesn't matter if you have $1 million or $0, you're adding 100 a month, right? So the best example then of a first order reaction is probably banking with interest rates. So if we think about a bank that has $100 and you're making 1% interest, let's say every month, which would be nice. If you have $100 in there, after 1 month, you have $101, right? If you have $1,000, then you're going to have 1% increase after a month, and you'll be increasing it by 10 because 10 is 1% of 1,000. So then if you have a very large number in there, you're getting a very large number every month. So the amount that is growing, or the amount that you owe in case of interest repayment, is going to depend on how much is there, right? So that it depends, and it depends one time. It's not that it depends on that amount squared, it's just it depends on that amount. A second order reaction, which really we're not going to deal with too much, but I just wanted to comment on it, is that's going to be as if your interest was calculated based on the square of how much money you had, right? So those get out of hand quite fast and go sharply downward or upward really quickly. I probably didn't make the best drawings here, but it's very sharp because of that second order. So how do we look at that in terms of the actual rate and the rate equation that we're going to use? Well, a generic rate equation, R of C, is going to be dc dt, so the change in concentration over time, and that's going to be equal to plus or minus for the decay or growth. Plus would be growth, minus would be decay. A rate constant, K, and then whatever concentration or amount, see a bank account, that would just be the dollar amount that's in there, raised to some power, N. And N is the reaction order. So if it's a zero order, we have, and we'll go into each of these in detail, but zero order would be plus or minus K times C to the 0. That means that's going to be 1. Anything to the power of 0 is 1. So it doesn't matter how much you have in there, it's just going to raise or lower by K. Okay? So in that case, that would be, the K would be the $100 per month. So when you think about these problems, and I'll show you in a minute, pay attention to the units, because you can learn a lot about the reaction rate and the order based on the units, and even tangibly so. Like I said $100 per month. You know that you have dollars per month as your units. That's your mass per time, or your amount per time. And if I say you get 1% per month, oh, those units are per month units. It's some portion, it's proportional to a per time unit. So it's a very different unit, and it turns out that first order are always time to the -1. And 0 is always basically that amount per time as the rate constant. Okay, so we'll derive that, make a little more sense of that. And again, none of this has anything to do with what type of container it's in. Okay, so we'll talk about the containers, the reaction vessels that are common, and how we then put these rates into mass balances after this. But that'll probably be for next time. Okay, so a 0 order reaction. Let's take a closer look at this. For, like I mentioned, for a 0 order growth or decay, that would be a decay. Doesn't really matter the steepness. That's decided by the slope. That slope is our K. So whichever one it happens to be, that would be our K value. That's a change in concentration per time. It's linear. And what I really want to show you is the rate constant here. We have to keep our units consistent, right? So earlier I mentioned R of C is going to happen in some volume. We have a volume times R of C. That's going to be mass per time. When we have an accumulation, V dC dt, let's say I'm growing some bacteria in my liter of water, then we have 1 liter times that change in concentration of bacteria per time. That's my accumulation, right? So the reaction is in some volume, so we have to have a volume term there. But that gives us mass per time because we have that volume times dC, which is, let's say, a mass per volume for dC. dt is just time. So when we have volume times mass per volume times all that divided by time, that goes to mass per time. Okay, so without the volume, that would just the rate itself would be a concentration per time. That's dC dt. Hopefully that's clear that dC dt really should be concentration per time, right? Okay, so then when tracking our units, when we equate the dC dt to this rate constant times c to the nth power, the rate constant has to change units based on what power the c is at. So in this case, this has to be equal. So let me come back to the dC dt. dC dt, this has to be something like milligrams per liter per second, okay, as the example I'm giving here. So that means that also has to be the same as k times c to the 0 power, but c to the 0 power goes to 1, and that ends up unitless because it's just kind of a unity. So then k must have those units. K must satisfy milligrams per liter per second. And what did I say about the dollar amount into a bank account for a 0 order? $100 per month, right? Some amount per bank per month. So I'm saying per bank for the volume, but you get the picture, right? So that's the amount per time inside that the volume of the bank account, we'll say. All right, so that means we have a way to know if you're given the units for a reaction rate constant, you know the order. And likewise, if you're given the order, you know the units based on this. So if we take the derivative, by the way, of either of these lines, it's going to be a linear flat line. We have no change in the change in time over time. So it's going to be a steady change. You know, that's $100 per month every year for a 0 order equation, right? The amount, that $100 is not changing. It does not depend on how much is in there. Okay, so a first order reaction then, we have the same thing happening. We need to get dC dt, that's our, in this example, milligrams per liter per second. That has to match with K times C to the 1 power this time. So K times C to the 1 power, that's K times C. C is already milligrams per liter. So K then has to be 1 over seconds, or seconds to the minus 1. Okay, and that's what I said about our first order reactions. And if you think about interest rates, what do you see on like a billboard or some advertisement? What's the unit? For any mortgage, interest, bank account, what was it?
Percent.
Okay, it's percent, but then what is like there's an acronym or like APR, yeah. So it's annual percent yield, right? So it's annual, it's on a percent, and it's a yield, kind of implying that it's based on how much you have there. But what are the units? It's per year. It's some percentage per year, but percentage is just a unitless, right? So it's really per year. So that's our first order rate reaction in your everyday world. So a first order then is going to look something like this or like this. And if you take the derivative of that, you get a linear line, and you can extract your K that way if we do a little bit of calculus. Okay, so that explains why we have that per second. So if you ever have a reaction rate constant in per seconds, then you know that's what's up. Does that make sense? Okay. I'm going to do the integration of these, I think, next time for you so you can see that. But for today, we'll wrap up with the second order. Again, these ones, very steep decline here, very pronounced. And then the derivative of that is going to look like a first order either way. And the units, we have the same thing. It's actually going to look a lot like first order units, because when we say that K times C squared has to be milligrams per liter per second, well, we have K times milligrams squared per liter squared. So K has to account backwards for that and adjust it backwards. So that means K is in liters per milligram per second. So it looks a lot like the zero order, which was milligrams per liter. It's just flipped, but also per time. So we don't really use second order reactions. I'll probably point out some to you. They're really pretty rare because, how often do you get a bank saying, "Oh, we'll take the amount of money you have, square that, and give you a percentage of that"? They're not going to do that, right? And you would never accept an interest loan that's going to do that to you either. So they're relegated pretty much to really, really rapid, radical type reactions in chemistry and some other niche areas. Okay, so that's good for today. We'll talk about the reactors themselves, do a little bit of the actual calculus to see, okay, how are we dealing with those reaction terms next time. Have a good weekend.